So section 2.1 is all about organizing qualitative data. So hopefully you remember qualitative data. That can also be referred to as categorical data. They're things that aren't numeric, they're categories. So when data is collected from a survey or designed experiment, they have to somehow be organized into a manageable form. Data that isn't organized is referred to as raw data. So there are several different ways that we can organize data. We can use tables, graphs, or numerical summaries, and we're going to talk about numerical summaries next week in chapter 3. So objective 1 is just be able to organize qualitative data in tables. So a frequency distribution is a great way to do this. This lists each of the categories of data and then the number of occurrences for each of the categories. So if we take a look, the next slide represents data that was collected by recording the color of M&Ms in a bag of plain M&Ms. And then we constructed a frequency distribution of the colors. So you'll see here listed someone took out an M&M, recorded the color brown, brown, yellow, red, 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 and they just did this for the entire bag. So a frequency table just takes the category, which in this case is color, okay, and it lists all of the possible colors. So brown, yellow, red, orange, blue, green. And then it looks like when they were doing this, they made tally marks to kind of keep track of each of the colors. If you're counting something yourself, this makes a lot of sense to do. Just create tally marks. And then once you're done with all of your tallies, you just add up the tallies, and that gives you your frequency. So for example, if we go back, there should have been 12 brown M&Ms, 10 yellow, 9 red, and so on. Now, the relative frequency is the proportion or percentage of observations within a category. And in order to find that, all we have to do is we take the frequency that we got for the category that we're talking about, and then we divide by the sum of all frequencies. So a relative frequency distribution looks pretty much like the other one. It lists each of the categories of data, except instead of listing the frequency next to them, it lists the relative frequency. So again, we have our data. We have 12 brown M&Ms, 10 yellow, and so on. So if we want to calculate relative frequency, the first thing we need to do is add all of these up. So if you add 12, 10, 9, 6, 3, and 5, we get 45. So that means that our bag of M&Ms had 45 M&Ms in them. So in order to get the relative frequency, all we have to do is take our 12 brown M&Ms and divide by the total number of M&Ms. So we get 12 divided by 45, you get 0.2667. So it's fine to leave it this way, or you can think of it as a percentage if that makes more sense to you. Remember to change from a percent from a decimal to a percent, you move your decimal place over to the right 2 places. So if you wanted this to be in a percentage form, you would change it to 26.67%. So that means that out of your bag of M&Ms, about 27% of them were brown, about 22% of them were yellow, 20% were red, 13% were orange, only about 6.7% were blue, and about 11% were green. Now, one thing to kind of note is that if you add up all of these relative frequencies, it should equal 1, because that is your whole or your total. Okay, objective 2 is to be able to construct a bar graph. So a bar graph is constructed either by labeling each of the categories along the horizontal or the vertical axis, and then the frequency or the relative frequency of the category goes on the other. Now, it's kind of typical to put the categories along the bottom or the horizontal axis, and then to put the frequencies along the y or the vertical axis, but it will work either way. The rectangles need to be of equal width, and then the height of each rectangle represents the category's either frequency or relative frequency. The shapes of these two distributions, frequency and relative frequency, would be the same for any given distribution. It just depends on the labels that you're putting on the actual axis that has the frequencies. So we want to use the M&M data to construct a frequency bar graph and a relative frequency bar graph. So we already have our frequencies and our relative frequencies, so this shouldn't be too difficult to do. So again, we have our data here, our 12 brown M&Ms. So if you look at what was done here, this is done either in Excel or Minitab or StatCrunch or something like that. And we can talk about how to do that in there in a minute. But we just have our colors along the axis here: brown, yellow, red, orange, blue, green. And then this is a frequency bar graph. So we have frequencies along the top, and you'll see we start at 0. The maximum was 12, so it looks like we went up to 14 just so that our bar doesn't reach the top of our graph. We normally don't like a bar to end at the top of the graph, so we'd like to leave a little bit of room there. And then you'll see these are all equally spaced. We don't skip any numbers. Our bars are equal widths, and then the heights represent the frequency. So you can see from here that we had 10 yellow, which we already knew we had. And you'll see there's a nice title here, bar graph for M&M color. So anytime you're creating some kind of bar graph or other chart, you want to make sure that you label your axis, okay, your x-axis and your y-axis. And then you want to make sure that you give your graph a title. This can be done fairly easily in Excel by entering data and then going and inserting a bar graph. Okay, it can also be done in StatCrunch, which lives inside of my math lab. You can export the data there, and then you can create a graph pretty easily doing that. We can also create a relative frequency bar graph. So what you'll see here is we actually have something where the shape looks pretty much identical. The only difference is this relative frequency right here. So you'll see that our label along our y-axis isn't 0 to 14 anymore, it's 0 to 0.3, so 0 to 30%. And then we've created kind of these equally spaced numbers. We have not skipped any numbers, and you can see that the brown M&Ms make up about 26% or 27% of our data. Yellow is about 22%, something like that. I don't remember what the actual number was, but you can see how you can get the percentages from here. Now, a Pareto chart is just a bar graph where the bars are drawn in descending order of frequency or relative frequency. So really all you have to do is you have to take your bar graph and rearrange it. So if you notice, I think the only one that was even out of order were these orange and green. I think they were flip-flopped. So here we have relative frequency along our y-axis, color along our x-axis. We have our highest frequency first, and we have our lowest frequency last, and it's nice descending, okay? Now, the reason that it makes sense to do something like this here is so that you can see pretty easily what your largest categories are. The other reason that it's okay to do this here is because there is no associated order. So brown, yellow, red, orange, green, we don't have a way of really ordering colors other than maybe the rainbow, which doesn't even really make much sense in any kind of ordinal way. If you were doing something where you had categories of freshman, sophomore, junior, senior, chances are that you'd want to probably leave them in that order for easy reading, okay? Or if you're talking about rankings within the military, you would probably want to leave it in that order along the x-axis. But when you have categories that don't have any order associated, you can kind of mix them up in any order that makes sense, and one of these would be to do this Pareto chart where you have it in descending frequency order. Okay, so if we'd like to compare two data sets, let's look at the following data. It represents marital status, it's all in millions, of US residents age 18 and over in 1990 and then in 2006. And we want to draw a side-by-side relative frequency bar graph of this data. So in 1990, you can see we had 40.4 million people who were never married. And this is age 18 or over. In 2006, 55.3 million. So what we're looking at here is we have two bar graphs that are side by side. We have these categories along here, our marital status, never married, married, widowed, and divorced. And we have relative frequencies along the side. And you can see that this kind of light blue color is 1990 and the medium or dark blue is 2006. So what you can see is that in 2006 we had a higher proportion who were never married, a lower proportion who were married, a lower proportion widowed, and actually a higher proportion who were divorced. So this allows you to compare kind of two different data sets that have the same categories and kind of see maybe how trends have changed over time or something like that. Okay, objective 3 is to be able to construct a pie chart. I'm sure you guys have all seen a pie chart before. But a pie chart is just a circle that's divided into sectors. Each sector represents a category of data, and then the area of each sector is going to be proportional to the frequency of the category. So if we look back at this data here, we have our marital status. This is now just the 2006 data. So we have 55.3 million people who were never married, 127.7 million who were married, and so on. Now, it's not shown here, but we would need to calculate relative frequency so that we get our percentage, and that was actually used in the last problem as well. You would have to add up all these millions, and then you'd take your frequency, 55.3 million, and divide by the total. That would give you relative. And then the percentages are used in the actual pie chart. So you can see we have marital status 2006. Each of these are labeled, so the blue is never married, the red is married, green is widowed, and purple is divorced. And then you'll see together they make up a whole pie. Okay, so we have 58% that are married, so that's more than half of our pie, 25% never married, and so on. It's always nice to put the actual labels here, these percentages. You can always add them if the chart doesn't come with them automatically. Again, this one looks like it was done in Excel, but you can also do this in StatCrunch, or if you have Minitab, you could use that. Okay, section 2.2 talks about organizing quantitative data, and we're just going to talk about the popular displays. So there are a lot of ways to organize data. We're just going to talk about the ones that are most widely used. So the first step in summarizing quantitative data is to determine if it's discrete or continuous. So if your data is discrete and there are not very many values of the variable, then the categories or classes are just going to be the observations, which is the same thing that we did with our qualitative data. But if the data is discrete and there are many different values, or if the data is continuous, meaning that, again, there are many different values, we have to create classes out of our data using intervals of numbers. So let's organize discrete data in tables first. So the following data represents the number of available cars in a household based on a random sample of 50 households. We want to construct a frequency and relative frequency distribution. So you'll see we have one household here that was surveyed that had 3 cars, one that had 0, one that had 1, and so on. So these are all 50 of our observations. It looks like the maximum is 5. Kind of see only one that's 5, and then we have several zeros. So you'll see the number of cars are listed 0 through 5. We have 1, 5. We had 4 zeros. We calculated frequencies just by tallying up each of those observations. And then if you add up all the frequencies, you should have gotten 50 because they surveyed 50 households. So in order to get our relative frequency, we just take our frequency and we divide by our total, which in this case was 4 divided by 50. So we get 0.08, which would correspond to 8% if you like to think in percentage form. So that means that 8% of surveyed households had no cars at all. 26% had 1 car. The majority, okay, or not majority, but the largest piece is 44% with 2 cars. So if we want to construct something that looks like a bar graph, it's actually called a histogram if we're talking about discrete data. A histogram is just constructed by drawing, again, rectangles for each class of data. The height is going to represent the frequency or the relative frequency. The width is going to be the same. And here's the difference between a bar graph and a histogram. The rectangles touch each other. Okay, so this really is not too difficult to create. Basically, all you do is you create a bar chart, and then you just get rid of the space that's in between these. The reason is that when we're talking about numeric data, it makes sense to have these all kind of connected, okay, as opposed to categorical data where we have it kind of all separated. So again, we have nice labels here. You can see that the biggest category is from the people who have 2 cars. It looks like there was 21 or maybe 22 people surveyed who had 2 cars. And again, here's a relative frequency. So instead of the actual number of cars, we have the proportions or percentages along our y-axis, but the shape remains the same. Okay, now this gets a little trickier if we want to organize continuous data in tables, because we can't just list all of the possible observations. So what we do is we create classes. Classes are categories into which data are grouped, and when a data set consists of a large number of different discrete data values, or when a data set consists of continuous data, then we need to create classes by using intervals of numbers. So The following data represents the number of persons aged 25 to 64 who are currently work disabled. So we have age groups here, 25 to 34, 35 to 44, 45 to 54, and 55 to 64. Now we could list all of the ages within these ranges and we could have numbers for each age, but we would have a lot of numbers. We'd have all the numbers between 25 and 64, which is just really too many numbers to look at. So what was done is these were grouped into kind of logical groups. This is a pretty typical age grouping that you might see. I want to talk about some of the terms that you're going to see in your homework. So the lower class limit of a class is just the smallest value within the class. So for example, it's 25 here. And the upper class limit is just the largest value within the class. So if you look, lower class limit for the first one is 25, lower class limit for the second one is 35, upper class limit for the first one is 34, upper class limit for the second one is 44. Now the class width is just the difference between consecutive lower class limits. So if you look from 25 to 35, if we subtract those, we get 10. So that means that our class width is 10. Okay, now let's organize this continuous data into a frequency and relative frequency distribution. So the following data represents the time between eruptions in seconds for a random sample of 45 eruptions at the Old Faithful geyser in Wyoming. So we want to construct a frequency and relative frequency distribution of our data. Excuse me. Sorry about that. So we have these various metrics. We have 728, 678, 723. So someone sat there for 45 eruptions possibly, or reviewed this later, and recorded the number of seconds. So from the first eruption to the second eruption, it took 728 seconds. From the second to the third, it took 678 seconds, and so on, and they recorded all 45 of these eruptions. So we want to look for the smallest and the largest data values when we're trying to create classes. So if you look back at this data, there are just too many different observations. We wouldn't want to just list all of the observations and then list their frequencies. It would be really difficult to gather any useful information from that. So what we're going to do is we're going to create some classes. So the smallest data value is 672, and the largest is 738. For the lower class limit for the first class, it makes sense to use basically a nice number that's a little bit smaller than your smallest data value. So 672 is not a very nice number, so it makes more sense to use 670 as their starting point. And we're going to go ahead and use a class width of 10, okay, and we're going to obtain the following classes. So we're going to have classes from 670 to 679, 680 to 689, 690 to 699, all the way up to 730 to 739, so we get our largest data value. So all we have to do is just tally up our observations again. So you just look through your observations, see what category they fit into. We have frequencies listed here, and then again, relative frequency is going to be this frequency divided by our total, which is 45. So you can see that it looks like the largest proportion is the 720 to 729 seconds. We have almost a quarter of all of the eruptions taking that long. And this is, again, time between the eruptions in seconds. So the choices of the lower class limit of the first class and the class width are kind of arbitrary. There isn't one correct frequency distribution for any particular set of data. However, some frequency distributions can better illustrate patterns within the data than others. So constructing frequency distributions is kind of like an art form. It's probably never going to be perfect, okay? You're not going to be maybe really great at it, but hopefully you'll get the hang of creating these so that you can start to recognize different patterns that exist. So use the distribution that seems to provide the best overall summary of the data. That's a pretty good kind of rule to go by. So if we look at this right here, they've redone this, all right, and we just have smaller class widths. So the class widths here are 5 instead of 10. You'll see that we don't have as many observations within each class, okay, and there are definitely more classes. Really, there are twice as many because our class width is now only half as big as it was before. So some guidelines for determining the lower class limit of the first class and class width. So we talked about this a little bit when we talked about our 672. but we want to choose the smallest observation in the data set or a convenient number that's slightly lower than the smallest observation. If you already know how many classes you want, then it's pretty easy to determine the class width. So generally, you should have somewhere between 5 and 20 classes. If you have a small data set, you don't want to have very many classes. If you have a large data set, you might be able to get away with having more classes. So if you know how many classes you actually want, you can determine the class width by taking the largest data value, subtracting the smallest data value, and then dividing by the number of classes, and that will give you your class width. Now, you might want to round to a nice number that's nearby, so you might not want a class width of 7. Maybe you want either a class width of 5 or 10. It's just a little easier to read the data that way. It makes a little more sense. Okay, objective 4 is to be able to construct histograms of continuous data. So we have, again, our time between our eruptions at the Old Faithful geyser. So using a class width of 10, it looks something like this. So if you recall, we created our frequency distribution before. Now we're just creating a histogram out of that data. So we have our class from 670 to 679. 680 to 689, and so on. And again, our bars are touching because we have numeric or quantitative data. We have the time in seconds along our x-axis. We have our frequency up here. So you can see that between 720 and 730, not including 730, we had 11 observations that took that long. And relative frequency, you can see for this one, they actually change it to a percentage. Okay, so this 25 represents 25%. Now, I'm not crazy about how these are labeled. I think these should probably have percent signs on them, so it's very clear what we're talking about. But you can see from here to here, the shapes are identical. All that we're changing is just the labels on our y-axis. And using a class width of 5, you can see how this histogram changes shape. So for this one, I think I like the look of the one that has the width of 10 a little better than 5. This one, you can see the shape of the distribution pretty well. This one, it gets a little choppy. It goes up and down kind of a lot, and you have a big kind of blank space here where you don't have any observations. So I don't like the class width of 5 quite as much as the class width of 10, but it's not correct to say that one is right and one is wrong. Like we kind of talked about, there's not a right or a wrong frequency distribution. It just takes a little bit of practice to kind of see which one looks nicest. Okay, objective 5 is to be able to draw a stem and leaf plot. So you guys have probably seen stem and leaf plots before at some point in your life. The digit to the left of the rightmost digit forms the stem, and then each rightmost digit forms a leaf. So example, a data value of 147 would have 14 as the stem and 7 as the leaf. So an individual is considered to be employed if they do not have a job but are actively seeking employment. So the following data represents the unemployment rate in each of the 50 U.S. states plus D.C. in June of 2008. So we have all of this data here. I think this 13 is a typo. These should just be states. So we have Alabama, Alaska, Arizona, and then we have their unemployment rates. So for example, we're in Indiana. The unemployment rate was 5.8%. And again, this is 2008, June 2008. Let's see if we can find our lowest. It looks like I see a 3.2. I'm trying to see if I see anything smaller. Yeah, I think North Dakota and Utah each have 3.2%. Oh, here's South Dakota, 2.8%. That looks like the lowest to me. And then the highest, there's 8.5%. That's the highest one I see. It doesn't mean that there's not another one, though. So we let the stems represent the integer portion of the number, and the leaves are going to be the decimal portion. So for example, in Alabama, the stem is going to be 4. Okay, and the leaf is going to be 7. So for Indiana, the stem is going to be 6, the leaf is going to be 8. So you'll see 2.8 was our lowest. Okay, so we have 2.8, that's how we read this. And then we have 8.5, that was our highest. I think that was Michigan. Now, one thing you'll notice is these are kind of jumbled right now, so it's kind of hard to see. After 2.8, the next observation is 3.2 if we're talking in numerical order, but it's kind of hard to see because these are all out of order. So one thing that you'd like to do is go ahead and rearrange these. So after you've created your stem and leaf plot, you want to rearrange the leaves so that they're in ascending order. So they start with the smallest on the left and they have the largest on the right. This is a little difficult to do when you're first organizing the data, so my suggestion is always just make it look like this first and then go ahead and rearrange each of your rows so that it's in ascending order. So construction of a stem and leaf plot. Step 1, the stem of the value is going to consist of the digits to the left or the rightmost digit. The leaf is going to be the rightmost digit. Step 2 is to write the stems in a vertical column in increasing order. So you'll see right here we have these in increasing order. Draw a vertical line to the right of the stems. Write each leaf corresponding to the stems to the right of the vertical line, and then within each stem rearrange in ascending order. Title the plot, include a legend to indicate what the values represent. When data appears kind of bunched together, we can use split stems. One thing before we talk about this, I want to go back to our stem and leaf plot here for a second. I want to kind of point out, this is nice because it still includes our original data. So this is a graphical representation where we haven't actually lost our raw data. So we can still read what all of the observations are. We can still read that there's a 2.8 and a 3.2 and another 3.2 and another 3.2. Whereas with histograms or bar charts, you can tell how, or not bar charts, but histograms, when we've classified our data that's been continuous, we lose some of that data because we just have bars that show us between which values how many observations are there, but you don't actually have the raw data contained in the graphic itself. So that's why this is kind of nice. Another thing I always like to point out, if you kind of tilt your head to the right while you're looking at this, you can sort of start to see that this actually looks like a histogram might. This is basically your bar height. Okay, so you have kind of this smooth curve here that you can see if you connected all of these. That kind of shows you what the shape of your distribution looks like. It's important to make sure that if you're looking at it like this, that all of your numbers are equally spaced, which they are in this example. So you can see that clearly the highest bar is when we have 5 as our stem. Okay, so let me go back to what we were talking about, which is split stems. So the stem and leaf plot shown below on the next slide reveals the distribution of the data a little bit better. So as with the determination of class intervals and the creation of frequency histogram, judgment plays a major role in deciding whether or not you should split your stems. There's no such thing, again, as a correct stem and leaf plot. However, some plots are better than others. So what was done here is 2.8 is our smallest observation, 8.5 is our lowest or our highest. So what happens here is you'll see that we now have 2 categories for 3, 2 categories for 4, 2 categories for 5, 6, 7, and 8. The only reason we don't have 2 categories for 2 is because our smallest observation was 2.8. So if you see, what is done here is that if we have leaves of values 1 through 4, we put them in this first stem. If we have leaves that are values 5 through 9, then we put them in the second stem. So it allows us to kind of break up our stems to see the distribution even better. And again, if you kind of tilt your head to the right, you'll see the shape of this distribution. You can see it pretty nicely here. And that way we don't have everything just in one long line. So the 5s, for example, were kind of the longest. So we have values, I had said 1 through 4, it's actually 0 through 4, and then 5 through 9 here. So again, this stem represents values of 3.0 to 3.4. The next one is going to represent values of 3.5 to 3.9. So once a frequency distribution or histogram of continuous data is created, like I talked about when we went back to that other stem and leaf plot, the raw data is lost unless it's reported with the frequency distribution. However, the raw data can be retrieved from the stem and leaf plot, which gives it a little bit of an advantage over histograms. Okay, objective 6 is to be able to draw a dot plot. So a dot plot is drawn by placing observations horizontally in increasing order and then placing a dot above the observation each time it's observed. So for example here, we have, hopefully you guys remember, we have this car data. Okay, we have our 50 households that were sampled and they were all asked how many cars do they have in their household, and that was all recorded. So what you'll see here, we have the title here, number of cars in households, and then we have cars here. We have 0 through 5, and then each observation is just a dot on our plot. Okay, so we have this nice little dot plot here. Now, I want to go back to this for a second and talk about when you might use this. You probably won't see this in a lot of real-world applications, but one way that I describe this to my class is that this is nice if everyone is one data point and you want to collect everything nicely and be able to draw a nice little graph pretty easily. So for example, if we're in a classroom and I were to survey everyone and ask how many households you have or how many cars you have in your household, I could just have everyone come to the board and put their own little dot exactly where it belongs, and then at the end of that process we would have this nice little dot plot. Okay, so it allows everyone to contribute one dot, and in the end we have a nice little graphic. Okay, objective 7 is to identify the shape of a distribution. So this is probably the trickiest part of this chapter. There aren't too many things that are very difficult in this chapter. This is probably the hardest. So the uniform distribution is one where the frequency of each of our values of our variables is evenly spread out across the value. Bell-shaped is probably something you've seen before. The highest frequency occurs in the middle, and the frequencies tail off to the left and the right of the middle. Skewed right is, these ones are a little bit counterintuitive. Skewed right means that the tail is to the right of the peak. Okay. Skewed left means that the tail is to the left of the peak. So if we look at these here, we have a distribution. This one's uniform. It's also symmetric. Okay, so symmetric means that if we drew a line right down the middle and we folded it over the left or the right, we would have pretty much the same shape on the other side. B shows another symmetric graph, but this one is bell-shaped, okay, because it looks like a bell. You probably have heard about bell curves if teachers have talked about maybe grading curves, okay, something like that. Now this is the one I like to call these a little bit counterintuitive because they take a little bit of time to get used to. But if you notice, skewed right, that means that it has a tail on the right-hand side of the graph. Skewed left means that it has a tail on the left-hand side of the graph. So all you need to remember in order to remember which skew is which is ask yourself, where is my tail? And then that is the appropriate skew. Tail on the right, skewed right. Tail on the left, skewed left. Okay, section 2.3. This is an important one for understanding how graphics can be misrepresented. This is probably something you have seen before in real life, okay? So objective 1 is to be able to describe what can make a graph misleading or deceptive. So here's a nice little quote here. Statistics, the only science that enables different experts using the same figures to draw different conclusions. Now, this is a little unfair because if you're doing it properly, we shouldn't be making different conclusions. However, it is definitely the case that people can take the same data and have very different conclusions based on the type of graph that they create. So the data in the table below represents the historical life expectancy of residents in the US. We want to construct a misleading time series graph that implies the life expectancies have risen sharply. And then we also want to construct a time series graph that is not so misleading. So our first one, this is a graph of that data, okay? B, this is a graph of the same data. Now you might ask, how is this possible? So take a second, see if you can identify the difference between these two graphs, because these are the exact same data points. Okay, what you probably noticed here, our y-axes are different. This one starts at 68 and goes to 78. This one starts at 0 and goes to 80. Now, it is okay to put a break in your graph, but you need to make sure that if you do that, you still label 0 down here, and then you actually show a little physical break. You show it by doing kind of like a little squiggly line here. So this makes it look like life expectancy has basically skyrocketed from 1950 to 2000. And this one shows that it has increased, but definitely not skyrocketed. All right, another example here. The National Survey of Student Engagement is a survey that, among other things, asked first-year students at liberal arts colleges to identify how much time each week they prepare for a class. So the results are from 2007 and they're summarized on the next slide. So we want to construct a pie chart that exaggerates the percentage of students who spend between 6 and 10 hours, and then construct one that's not misleading. So we have our hours here and we have relative frequencies. This was already done for us. Right here is where we have our misleading graph. We have the 6 to 10 range. It is right out front and this piece looks really, really large. If we look at this though, what we can see is that although this piece is pretty large, the purple piece looks either just as big or maybe very slightly smaller. If we go back to our data, we'll be able to see, okay, it's just very, very slightly smaller. But if we look here, the purple piece looks really small in comparison to kind of this tan piece here. And the reason is because of the 3D graphic. So when we create something that's two-dimensional like this one here, we can see everything laid out fairly nicely. It's pretty clear which one is the largest piece. But if we look at this, we definitely have some kind of misrepresentation going on here. It's the correct data, but this tan piece in front looks really, really large. So some guidelines for constructing good graphics. You always want to make sure that you title and label the graphic axes clearly, providing explanations if needed. You want to include the unit of measurements and a data source when appropriate. Avoid distortion, never lie about the data. Minimize the amount of white space in the graph. Use the available space to let the data stand out. If scales are truncated, you have to clearly indicate this to the reader. So that was what I was talking about. If you're going to have a scale start at the number 50, you still need to include 0, and then you need to put a little line that indicates that you did not include all of the values. You want to make sure that you avoid clutter, such as excessive grid lines, unnecessary backgrounds or pictures. You're not trying to distract the reader, you're trying to show them the actual data. Now avoid 3 dimensions. So these might look really nice, but they kind of distract the reader and they often lead to misinterpretation of the graph. And don't use more than one design in the same graphic. So some graphs use a different design in one portion of the area or one portion of the graph to draw attention to that area. You don't want to try to force the reader to any specific part of the graph. You'd like to let the data speak for itself. Avoid relative graphs that are devoid of data or scale.